All right, so the missed topics. Now, they weren't completely missed, but they were sufficiently not emphasized that it made a big difference on the test, I think. And the first of those is system of relative mass. So it was one of the free response questions, and of course the whole idea of relative mass showed up in at least two other questions as well. There were two multiple choice questions that had to do with this. But I think this phrase, system of relative mass, threw a lot of people off. There were some people who told me how they calculate average atomic mass. There were people kind of all over the board on this one. And I think that I'm not sure that I ever actually used this phrase, system of relative mass, except possibly in the context of Dalton. All right? But we have a modern system of relative mass, which is based on carbon-12, that I just briefly touched on. So I want to talk a little bit more about that. What I realized when I was looking across Moodle and seeing what we did, and I had actually posted a video that went into a fair amount of depth on this topic, but I didn't require you to watch it. It was from last year. It was a lecture, like 50 minutes long. It was called Dalton and Relative Mass or something like that. But I didn't do that in class, and I didn't require it. So I want to talk a little bit about it now and then put it on the quiz tomorrow in some form. We did discuss John Dalton and Dalton's system of relative mass, and some of you discussed this, so I could tell that you remembered what we had talked about with John Dalton. Remember, he said that hydrogen is equal to 1, and then he compared everything to that. So hydrogen equal to 1. This we could call his standard of measure. So basically he picks hydrogen, which makes a lot of sense because it's the lightest one, and he said that is 1 unit, and I'm going to compare everything else to that. So then he compares all the other elements to hydrogen, or at least all the elements he had enough data on. And gives them a mass equal to their mass ratio with hydrogen. So that's what Dalton did. Thank you. Okay. So that's not what Dalton did, but that is a system of relative mass. And I think I might have mentioned that you could do this. I could say, all right, I'm going to be 1 unit, and then somebody who's half my mass will be 0.5 units. Somebody who's twice my mass will be 2 units. Somebody who's 3 times my mass will be 3 units, and so on. Now, it can get a little more complicated if I don't use the number 1. So what if I make a system of mass and I say, my mass is 100 units exactly. Now somebody who's half my mass has a mass of 50 units, right? And somebody who's twice my mass has a mass of 200 units. Now this is what happens in the modern system. Modern system of atomic masses. In this system, the carbon-12 isotope is assigned a mass, and this is what I think I briefly mentioned, but didn't go over it in sufficient depth, is assigned a mass of exactly 12 AMU. Now this is important because our system of atomic masses now, when you look at the periodic table, and those masses are relative masses. They're averages, that's important too, but they're still relative. Relative to what? Not to hydrogen being equal to 1. They are not relative to the mass of a proton. They are relative to the carbon-12 atom being exactly 12. That's what they're relative to. So they're all compared to carbon-12 being exactly 12. Now, that raises kind of another issue, and that is this number 12 right here. We learned that this is called the mass number. And again, it's one of the cruel things that chemists have done to us. One of the many cruel things that chemists have done to us in the past centuries. And that is to call this the mass number when it is not a mass at all. At all. It is not an approximate mass. It is not the mass of anything. When you see that word mass in the context of mass number, you're thinking to yourself, those wicked chemists have tricked us. It is not a mass. This number is, instead, it is a count of what? Protons plus neutrons. Neither of which is exactly 1 AMU. Now this brings up another confusing point on the test. When we made that long table and I wrote relative mass and then I put each of the particles, I wrote 1 for proton. But what I was doing is, and I know it was confusing, but I was saying if we assigned a proton a mass of exactly 1, then a neutron would be approximately 1. I wasn't saying it was exactly 1 AMU. In fact, if you think about it, if you think carefully about this, if carbon-12 is exactly 12 AMU, and if a proton and neutron are not exactly the same mass, then a proton can't be exactly 1 AMU. Follow me? Because you can't have exactly 6 plus something that's not exactly 6 equal exactly 12. Yeah. Because they're so small, they don't affect the mass much in general. Yeah. All right. Now, although it's a good question, when you talk like that table I showed you before where they show like the 11 sig figs, they would definitely affect it there. And I'm not really sure what they do with the electrons in those cases. Yeah, I'm not sure. So anyway, neither of those protons or neutrons are exactly 1. Something else funny happens. When you build a nucleus, some of the mass goes away. And it actually becomes energy that is called the binding energy of the nucleus. That was one of the questions on the test. I pulled that one also because we didn't even talk about binding energy. So I just took that one totally off. So there's a few reasons why this is not a mass. But the main one is that it is simply a count of things. Now the confusing thing becomes when I see something like this, carbon-13, and then I see mass, and I see 12.989, I'm making this up, ... AMU. This can make you feel like 13 is an approximation of that. It is not. It is really it's not a coincidence, but it's just an artifact of the fact that we chose carbon-12 to be exactly 12, and because carbon-12 has 12 nucleons, 6 protons, 6 neutrons, this just kind of works out that way. So every time the mass is going to be very close to the mass number, but they are not the same thing, and the mass number is not the mass rounded or estimated or anything like that. Okay? So that is another issue. And now there's another issue too that's in connected with this that is a point of confusion. This is a periodic table. All right. Notice that this number is not exactly 12. Why? Lewis. Okay. And? they do. They're different isotopes of carbon. They have different masses. And so what's this number got to do with it? What is that number? Is that the number of one of them? No, it's the number of... Okay. Average, right. So this is average mass. And by the way, it is a weighted average. The most common mistake on the atomic mass problem is for people to just do a straight average. They just take the masses and average them together, like you would any three numbers. Now you have to do a weighted average. It's the mass times the abundance in its decimal form, plus the mass times the abundance, plus the mass times the abundance. Average mass of all isotopes. You will not find that number 13 or 12 on the periodic table. Just like if you're looking at uranium-235, you're doing a nuclear equation, and you look for this on the table, you won't find it. It's not on the table. It's a mass number. They don't put mass numbers on the table because there's a lot of them, and it would be very difficult to make a periodic table that has all the mass numbers of all the different isotopes. I suppose you could, if you made it big enough, you could fit them in there. For each element, you could list all the isotopes. So it's conceivable you could do that, but you generally don't see it. Some of these have 7 or 8 different isotopes. So that's just some other things I wanted to clear up about the difference between mass and mass number. The other thing is when you write it like this, okay, that's the same thing as writing it like that, carbon-12. And this, of course, is atomic number. Questions? All right, which brings us to the other issue I want to talk about was fission versus decay. Now, I think you had sufficient coverage of these different reaction types to be able to distinguish between the two. They were in separate videos, actually. So decay was the first video that you watched, fission was the next, and fusion was the third. So they were actually in 3 separate videos. So they are 3 separate processes. Fission is not a type of decay. And so that's a common error I saw, as people saying that fission and fusion were types of decay. But they're not. They're not decay at all. So that was the first thing. They're not the same. They're not the same thing. And then the second issue was that it is fission that happens inside a nuclear power plant. In a nuclear reactor. Now, there's probably some decay going on as well, but it's not decay that's creating the power in a nuclear reactor. It's fission. And so you need to know the difference between those. And so I'm going to put something about this on the quiz tomorrow as well, fission versus fusion. These are all going to be multiple choice. It's going to be maybe 5 questions, something like that. It's going to be quick. So fission versus fusion. Fission versus decay, and then this is what happens in a nuclear reactor. Now, I've realized too that I didn't show you this little game on here. Some of you might have seen it. There's a little game up on Moodle. It's called Run a Nuclear Power Plant. And so I just want to show you that, just to emphasize the point here about what's going on in a nuclear power plant. And maybe some of you, it'd be nice if some of you learned about this as you were writing your papers, but it wasn't necessarily a requirement to, you could still have a good paper without knowing exactly how nuclear power works. But if you go to this site here, you can try it out. It's a little risky because we're running Java. So this is an ancient style of nuclear power plant. The new ones probably don't look much like this at all in their design. Over here you have the reactor core where we have the uranium fuel. So this would be uranium-235 isotopes that have been purified and concentrated. So just one isotope essentially. Uranium-235 is the fissionable isotope of uranium. 238 won't work. 238 is the most common. If you look at the mass of uranium on the table, it's around 238. So they have to get the uranium ore, and then they have to extract the 235 out of it. So not only do they have to extract the uranium from the ore, they have to purify the 235 and get rid of the 238. All right? So anyway, those are the black lines here. Those are the fuel rods. And then these gray things that come down, those are called the control rods. And like I said, this is old technology. I don't know what they do today. But the control rods absorb neutrons, and so they slow the process of fission down. Because neutrons initiate fission. And then each fission reaction produces neutrons, which initiates more fission, which produces more neutrons, which initiates more fission. And this thing will go on at too fast of a rate if you don't control it. So you can lower those rods in here, soaks up the neutrons, and it slows down the process. The newest technology, and I don't know if they actually use this or not, is they have fuel rods that as they get hotter, their density decreases. They expand and their density decreases to the point where the chain reaction stops. So they're self-regulating. So like theoretically they can't melt down because as they get hotter, they will automatically slow the reaction down. It's a negative feedback system. So this is kind of fun though because we have these different sequences of things that can go wrong, and then you have to figure out how to stop it from melting down. So I hit sequence 1, things cranking out power. Oh, we had a blowout in the turbine. So what's happening now? My pressure is going down. This is my pressure because the steam is getting out. See, this thing is, it's getting hot, it's heating up the water, and it's making steam, which runs the turbine, which runs the generator. But the steam right now is escaping the system. And so you can see my water levels going down. Oh, and now my pump broke. And now my water's all evaporating from my core and it's getting too hot. The level has gone down below the fuel rods, and I have meltdown. So, not good. We better do better next time. Start sequence 2. What happened? Oh, our pump broke. What do you want to do? Close the valve? Open the other one. Start the pump. Quick. Too late. We got to be quicker next time. We should have started this other pump. By the way, this does show how the cooling system, see this right here is the cooling system that comes in. The cooling system is separate from the water that's actually in contact with the uranium. And so this water goes out into those giant cooling columns that you see. You see those huge round columns at all the nuclear power plants. And you see the steam coming out of them, or the water, condensing water coming out of the top. Those are the cooling towers. Sequence 3. Let's see if we can do better here, folks. We're not... What happened? Oh, the cooling pump. What do you want to do? What? Name them. They have names. What do you want me to do? They have names. SV1, WV1. Oh my goodness. You guys. Shut everything. Oh well. Oh well. Better luck next time. It is. Yeah, I don't know if it's turned on though. Let me make sure you can see it. Yeah, you are now qualified to be the plant manager at Millstone. Not. Actually, you just failed your interview down at Millstone because you panicked mainly. Let's see. There it is. Yeah, you should be able to see this. So it says cool run a nuclear power plant. All right, there's one other thing I want to talk about, although I'm not going to put it on the quiz tomorrow because it wasn't a major issue with respect to your grades. And that is, some of you didn't see this, some of you got a slightly different question, but this is a molecule. Okay? In this molecule, this is one molecule, okay? But in this molecule there are 24 atoms. So if a question says how many atoms in, let's say, 1 mole of C6H12O6, and I know it was kind of tricky. I mean, I could have bolded the word atoms or something like that to make it easier, but how many atoms in 1 mole of C6H12O6? The answer is not this. There's that many molecules, all right? But because there's 24 atoms in a molecule in this case, by the way, the iron sulfate one had 17 atoms per unit, per formula unit, so it was very similar. There would be 24 times that. Okay, I'll have to, if you could just send me those particular problems if they were on the quiz or whatever, I'll have to correct them. I didn't realize that. So I know that the Mr. Gooch worksheets, he confuses molecules with formula units. I don't think he confuses molecules with atoms. All right. So anyway, it's important to make that distinction. I know that one reason that people get confused about this is because the idea of a mole always being 6.022 times 10 to the 23rd, whether you're talking about molecules or atoms, that's true. A mole is always 6.022 times 10 to the 23rd, whether you're talking about molecules or atoms. That being the key phrase. What are you talking about? So a mole of atoms is 6.022 times 10 to the 23rd atoms. A mole of molecules is 6.022 times 10 to the 23rd molecules. But that doesn't mean that if you have a mole of molecules, you always have a mole of atoms. Okay? So I know it's confusing. The whole concept is difficult, but it's an important distinction. And it's very important to know the difference between atoms and molecules. All right? So, any questions about this stuff? Quiz tomorrow. And what we're going to do on the quiz is something about a system of relative mass. Something about mass numbers versus masses. Now, mass number versus masses, it wasn't that I saw that you guys had a big problem with it on the test. It's just I know that some people have been confused about it from discussions, and I want to make sure you get that one. And then lastly, decay versus fusion. And so if you feel like you need to go back and watch the appropriate videos here, you can watch the long lecture that I put up there. It is, let me show you where it is. It's back here somewhere. Must be in this one, sorry. Right here. Lecture vid, Dalton's relative masses. So this one right here will give you some more background on relative mass if that's what you're looking for. Relative mass in parts of the atom. Maybe clarify that a little bit. Okay, somebody had a question? Yes, Amy. Yes. Thank you. Fission. Decay versus fission, which is happening in a nuclear power plant. You know, hopefully someday we will have nuclear power that's fusion-based, but we don't right now. And the Brightstorm girl, I think she did a good job talking about these things, but because I didn't review it in class, that what happens in a nuclear power plant, I thought it'd be good to give you another shot at that. All right? Any questions? Okay. We are going to